Well, thank you all so much for joining us for Navigating in Space. Solar System Ambassador David S. Ball, who's a volunteer educator with NASA's Jet Propulsion Laboratory, will discuss navigation in space. Determining where we are and how to get places has been an age-old challenge on land. This was compounded as humans took to the sea and into the air. And the next great challenge, Ball will discuss how we find our way in outer space. So David has served 26 years in the U.S. Air Force, and he retired as a lieutenant colonel. So for all 50 of us or so who are watching live and the many more that will watch the recording, let's thank David for his service, and let's give David a big virtual round of applause for being with us today. David, you can take it away.
Oh, super. Thank you. Thank you, Robert. I'm so grateful to the Tewksbury Library. I mean, you're able to reach so many people and so much more than we could possibly do in person. And it's an opportunity to share interests and to be able to talk about things things that we're curious about. And so what I wanted to talk about today, let me share my screen here, is I was thinking a little bit about how we navigate in space. And it's interesting to me, and it's not only had an impact on how astronauts get places, but it's had an impact on us in a broader society. So let's talk a little bit about navigation in space. So when you think about getting from one place to another, let's start out with walking. So you're standing in one place, you want to go to someplace else. Maybe you have a compass and you go in that direction, or you have a map and you're making lefts and rights, and you get to where you want to go. And so the walking, fairly simple. We've been doing that for a while. Same thing with driving. Maybe it's a little bit different because you maybe can't get there from here because it's a one-way street, or because you're going a lot faster, or, so there are some little things that are a little bit different about driving places than walking. And then once we took to the ocean, maybe there are some different challenges there. I mean, about which way the wind's blowing, or whether there are currents, or, some different things about navigating when you're at sea. And then when we look at navigating in the air, different complexities, different challenges, different opportunities. And then when we're talking about space. So starting with at sea, I read an interesting book by Dana Sobel called Longitude. And in it, they talk about one of the big challenges of navigation in the 18th century. So over here, we have a map of the west coast of Africa, and you can see the incredible amount of detail of all of the inlets and rivers associated with the west coast of Africa, because that's where the ships were able to figure out exactly where they were, so they're able to map it. And you can see these lines where, okay, so somebody has a compass and you say, well, okay, I know where I am, and I'm kind of headed in this direction. And so that's the state of the art for navigating at sea. So there are some challenges when you're navigating on the water. So waves, wind, war, weather, all these things have some different kinds of challenges. So different from being like along the coast. You're sailing along and there's the coast to the right. You could do that. That's basically a straight line. But if you're in the open ocean, you have to do things by dead reckoning. You have to estimate, where your position is, because you're in the middle of a big ocean and you can't tell exactly where you are. And sometimes the charts aren't very good, and there's a question of instrument accuracy. So let's look at how it is that we were able to navigate at sea. So it turns out that if you have something called a sextant, here, we've got this right here, and you're able to measure the angle between the sun when it's at its highest, so at noon, and the horizon, you can determine how far away you are from the equator. You can say, well, I'm 10 degrees higher than the equator, and this is our latitude, okay? And it goes from 0 at the equator, and it goes to 90, which is the North Pole, or 90 south, the South Pole. So navigators at sea, all they had to do was figure out when the sun was at its highest, take the angle, and they'd figure out, how high they were up on the globe. Now, east-west, understanding the longitude, different story. And really what would be super useful is if you were able to have a clock that told you what the time is at a reference place. So let's say Greenwich, England. And you could take that clock with you on your voyage, you could figure out where you were in east to west, so the longitude. So in 1720, this is about the time that the Admiralty in Great Britain, which was a great sea power, kind of put out the challenge and said, we need to solve this problem. We need to understand navigation, east-west navigation at sea. So this thing over here on the left, this grandfather's clock, this is a clock that was made in 1720. All right. So it's made of dissimilar metals. It's a big wooden thing. It's got this long pendulum. You can imagine you put this on a ship and it's exposed to extremes in humidity and temperature, and the boat is rocking and it's getting wet and all this kind of stuff. So it's impractical. It's not going to tell a reasonable amount of time. So John Harrison, who was working at this time on clocks, he made it kind of his life mission that he was going to create a clock that you could take on the ship. All right. So this one here, this is H1. This thing here is H2. This is H3, and this is H5. And by H5, it looks like a pocket watch, right? I mean, it's sealed against the elements, and many of his timepieces didn't have any lubricants, and they were incredibly accurate. So what we're talking about is a chronograph, a chronometer. And here you can see in a box one that was used, and they would set these things when they were leaving on their voyage to the time in England, and they were able to compute where they were on an east to west basis. So now let's look at if we were flying. Okay, well, there are challenges to air navigation. So, if you're trying to fix where you are, let's say you're flying out over the water, or you're flying over the water at night or in poor weather, be quite difficult to figure out where you were, right? And, if you wanted to use like celestial navigation, you're trying to use the stars to try to figure out where you're at. And you're a solo pilot, and you're in an open cockpit, and the wind's coming at you at 100 miles an hour, and it's freezing, and you're trying to shoot pictures of the stars, and it's cloudy. You could imagine there are some real problems and the airplane's going fast, and it's rolling all over the place. So you can imagine there are all kinds of challenges associated with trying to do navigation in the air. So here are a couple of ideas of how you can do it with airplanes. So the first one is called pilotage. And so what that means is, okay, you're in your airplane and you're flying along, and you look down and you see railroad tracks. So if you follow those railroad tracks, you're going to get to wherever it is that those railroad tracks go. That's pilotage. All right. But let's say, for example, look at the one below pilotage. Let's say you're going from Phoenix and you want to go to El Paso, but you don't have railroad tracks that go between there. And by the way, one of the jokes with pilots is they say, do you know what IFR stands for? So IFR means instrument flight rules. That's when you use your instruments to figure out how to get places, as opposed to pilotage. But IFR, they say that means I follow roads. So if there was a road going there, you'd be able to figure that out. But underneath the one that says pilotage, and we're going from Phoenix, we're going to El Paso, and it turns out that there isn't a railroad track that goes there. You could say, well, okay, I've got a compass, and El Paso is in this direction, and my airplane flies at a certain speed, and I've got this much crosswind, and I know there are certain landmarks that I'm going to see as I'm flying. So, for example, I know that I'm going to fly over this river, or I'm going to be able to, when I get to the river, I look to my left, there's going to be a reservoir. So you could figure out, you could say, okay, I'm starting in Phoenix, I'm going in this direction, I'm going at this speed, there's this much crosswind. And after 23 minutes, all of a sudden you reach the river and there's the reservoir and you've got this new fix, this, I know where I'm at right at this second. So this is called deductive reckoning, or they call it dead reckoning. And it's a way of getting places if you don't have a railroad track that takes you there. So dead reckoning, that's something that all pilots learn to do. And then there are electronic things that can be done in addition to pilotage and dead reckoning. So there's one called flying the beam. So you could have a radio compass where you've got a transmitter that's at an airport, and it sends out Morse code. So when it's sending out this Morse code, if the signal that you get comes back and the Morse code is saying A, what it's telling you is that the signal is to your left and you need to turn left. Now, if you're flying along and it keeps saying N, 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 what it's saying is that the beam is to your right. You need to turn right. And what they say is that if you're in the right place, the N and the A cancel it out and you get this tone. And they call that flying the beam. So in the 1920s and 30s, that's a way that you could get places, that you could tune into this and you'd be hearing the A or you'd be hearing the N, and that would kind of, that would get you there. And there are radio compasses, and down here in the lower left, we've got a guy who's using a sextant, right? But he's using a sextant for the stars, and he's doing it from an airplane. Now, you couldn't really do this if you're a barnstormer in a biplane, but imagine that you're in a B-29 and you're flying across the Pacific, and it's at night, and all you have down there is water. You don't have pilotage. Dead reckoning can be kind of dicey, and you got a crew of 12. So you might have a guy who's a navigator, and he kind of goes up there and figures out where the stars are and the angles and things like that. Gets an idea whether or not they're on track. And then down here, you can see with this helicopter, they're taking all kinds of measurements that are coming from satellites. And so what a satellite is doing is it's spinning around the Earth, and it has a very precise clock in it. And it's able to do a bunch of triangulation with ground stations and figure out exactly where it is. And it's sending that signal to your GPS receiver and telling you where you are. So now with GPS, and we have this, not just in airplanes, but you have it in your car, you have it on your telephone, you're able to tell pretty darn close, where you are in the world based on having 3, 4, 5 different satellites sending information saying, well, this is the angle, this is where this satellite is, and this is where you are. But how about when we're talking not about walking in a straight line, or driving a car, or being, at sea, or in an airplane? Now, let's say we want to fly in outer space. Well, different kinds of challenges, right? Because not only do you have the motion of the spacecraft, which might be going, thousands of miles an hour, but you've got all these pieces moving, right? When you're on the Earth, even though the Earth is moving, everything's moving at the same rate, right? So that's not really an issue. But if you're in space, the moon is moving at one speed and the Earth at a different speed, and they're going in different directions. And, you've got all these things interacting. So you've got this motion. And then the distances are just tremendous, right? And, unlike in pilotage or dead reckoning, you don't, when we're going from here to the moon, there's like nothing in between there, right? So it's not that we come up and we get a fix and we say, okay, we're on track. So you have to do these remarkably big distances and be very accurate when you show up. So this is a challenge. And communications, like during Apollo, a lot of the navigation was done from the ground, and the ground would send up updated information to the Apollo guidance computer. And if you had problems with communication, because radio communication is line of sight, which means that if your spacecraft is on the other side of the moon, then you can't talk to anybody. Or let's say something kind of goes wonky with communications, that's a problem, right? And then there's gravity. You know, you don't really think of gravity as being a problem with navigation, but it turns out that if you're flying along through space and you come close to a big body, like you're flying by Mars, all of a sudden it's going to kind of grab you and pull you in. So you have to take that into account in terms of managing trajectories. And so some of the things that we're kind of used to, like pilotage and dead reckoning and having a compass heading and having charts, aren't really as useful as we'd like them to be. You know, when we're on the Earth, it's got a big magnetic core, and you could take your little compass out, and you know that's a direction. Well, on the Moon, it has a very weak field. It has a crust. It doesn't have a core, and so compasses don't really work. And they also have a thing called mascons. So they've got mass concentrations of material that change the amount of attraction associated with two bodies, like a spacecraft and the moon. So we have some challenges there. So what I wanted to introduce you to, this is the input-output device for the Apollo guidance computer. And you know, it's become kind of the thing to say that you know, I have more programming power or more memory or something in my Apple Watch than they had on the computer that went to the moon. And for those individual kinds of things, like how much memory, I'm sure that's true. But this was a remarkable piece of engineering. At the time that this was being considered, which was in the late 1950s and early 1960s, a general purpose computer took up a room. It was room size and weighed several tons. So here, where every pound that you lift and you take to the moon requires a lot of fuel, you have to keep making the rocket bigger and bigger for every pound you want to lift. You couldn't lift something that was the size of a room and weighed several tons. So the challenge to Apollo was they said, okay, we want you to make a guidance and navigation computer that's going to do things on rendezvous and helping you land on the moon and all this kind of stuff. But we want it to fit into a space that is one cubic feet in size, and it weighs 50 pounds. And not only that, we want it to be something where it's going to be vibration proof, right? Because you can imagine, you know, if you had a computer in a building and all of a sudden you had the building shake, you know, you could definitely hurt your computer. Or let's say that there were big changes in temperature or humidity or pressure or barometric pressure. All of these kinds of things impact electronics. But you needed to make this thing bulletproof. I mean, so much so that not only would it operate if, you know, 7.5 million pounds of thrust underneath it all of a sudden took off and this thing went to the moon, but also that it wouldn't get hung up and you can't repair it in space, right? I mean, initially they were thinking, well, maybe we'll send up some tools and we'll send up some spare parts and we'll teach these guys how to like swap out boards and things like that. And they decided, you know what? This thing just has to be bulletproof. And so what they ended up doing is they would take the computer, figure out all the wires, and then they would pot it. They'd put it in a resin so that the things wouldn't shake loose. And so this is the input-output device for the Apollo guidance computer. And the way in which they had the astronauts interact with the computer is they would look at things and call them verbs and nouns. So a verb is do this, And a noun, well, a verb is, this is what I want you to do. And the noun is, I want you to do it to this. Okay, so a verb might be something like, I want you to display something on the computer. And the noun might be, this is what I want you to display. So I want you to display what the closing speed between two spacecraft are. So the verb might be display closing, delta velocity or something like that. And you can see it only has a couple of buttons. And so the astronauts, they're all in their spacesuits and they got these big gloves on and stuff. So you can only just have a couple of buttons, and it was remarkably bulletproof. It was a wonderful, and even when it had problems, like it would have a program alarm or something like that, instead of locking up, what it would do is it would immediately reset itself. It would say, what's the most important thing for me to be doing? I'm going to do that. And if you've got some other request, I'm going to do that request in the background. And if I have enough bandwidth, I'll do it. And if I don't, it's just not going to happen. And so that's what this input-output device is. And then these are the codes. So these are the different programs. So the first couple of ones, it's divided between the command module, where the three guys were in when they launched from Florida, and then the lunar module, and then there were some other codes. So for the command module, there would be stuff to initialize it, and then things for navigation, and when the computer was supposed to fire the engines, different aborts and backups and things like that. And for the lunar module, so for example, when they're in orbit and they're ready to go and land on the moon, they'd put in P63, which is program 63, which is the braking phase. And that orients the big Bell engine underneath the lunar module to be in the direction of flight. And they fire that engine for 7 or 8 minutes, and it loses velocity, and the lunar module, goes down to the surface of the moon. So getting back to navigation and how we know where we are. If we don't have a map, if we don't have fixed points that we're going to, like we do on the surface of the Earth, we have to come up with something else. And so this is ST-124. This is the 124th iteration of this inertial navigation system. And this particular one that we're looking at is part of a 3-foot high band that's sitting on top of the third stage of the Saturn V rocket. And this was built by IBM. And what it consists of, these are accelerometers and gyroscopes. And so what happens is you have a wheel, and as something happens, like let's say the rocket takes off, that imparts angular motion into this wheel. So the wheel spins, and in doing so, that gets converted into an electrical signal. And that signal goes to the inertial navigation system and says, okay, I'm being pushed in this direction by this amount of force for this amount of time. And the inertial navigation system says, okay, I'm going to remember that. And in addition to remembering that we went up for an hour, and then we took a left for 20 minutes, it also sends an electrical system back to the gyroscope and gives it an opposite direction torque. And what that does is it makes the platform stable. Okay, so you got a stable platform, it gets angular momentum, it gets converted to an electrical signal, that signal gets recorded, and it kind of keeps track. This is where I went, and so this is where I'm coming from, this is where I must be. And so it's this combination of these accelerometers that are sitting in this gyroscope, and you've got this stable platform, but it's recording all of the different pushes that this spacecraft is having. But what in order to get this inertial navigation system aligned, we need to know where we're starting from, right? I mean, if I told you that I knew all the lefts and rights and ups and downs that we did, but I couldn't tell you where we started from, you wouldn't be where you thought. You wouldn't know where you were, right? So you have to start by knowing where you are. So we have, we've got one-dimensional space, which is on a line, and two-dimensional space, which is on a plane, and three-dimensional space, which is left, right, forward, back, up, and down, right? We got 3 dimensions. So when we've got the rocket, so here's launch pad 39A at the Cape. On the y-axis, that's north and south. So you can determine where you are on the planet and say, between the North Pole and the South Pole, this is where launch pad 39A is. Now, east to west is the z-axis, and we can also determine that, right? We can say how far away are we from Greenwich, England, and so with a latitude and longitude, and you can see it's got a couple different systems here, one called DMS, one is digital, 28.608, and geo references and all this sort of stuff. But it's all doing the same thing. It's a plane on the Earth, and it's saying that in these 2 dimensions, in the z dimension and the y dimension, I can tell you where on the planet I am. And the way they did that in the Saturn V is they had these 2 little pendulums that were located inside the navigation unit, and they're weighted iron rods, and they're floating on a pocket of air. And the Earth is kind of rotating, and the rods are being kept perfectly flat, and so the gimbals are kind of telling the gyroscopes where you are, and so you're able to tell exactly where you are, east, west, and north and south. But here's the question. That part is kind of like the latitude thing. It's something that it wasn't all that tough to do. The question is, how do you do the X direction, and why is that a thing? So the X thing is the direction up. So, and I wrote this here. I said when the origin and the destination have different velocities. So when we're sitting on this globe, all right, and we think of the Earth as, we know it's a ball, but when you look outside, it looks like a flat piece of paper. So when we're on the Earth is rotating at a speed of 1,000 miles an hour. All right. And so if I look between here and a mile down the road, it's not a problem because I'm moving at 1,000 miles an hour. That place is moving at 1,000 miles an hour. Anything that we're talking about that's on the surface of the planet, not a problem. But what would happen if you picked a point, instead of it being a point, a mile east of us, but a mile above us? All right. It's a problem because the Earth is spinning at 1,000 miles an hour. And so now when I say I'm pointed at like a particular star or something, an hour from now, I'm not going to be pointed at that star, right? Every 24 hours, the Earth turns all the way around. So what direction you're pointing is changing all the time, all right? And it's really important, particularly if we're going to go to the moon. It's 338,000 miles away. It's real important that we know exactly where we are and that we're pointed in the right direction. So how do you do the x-axis? And that's what I wanted to show you. So that we got the z and we got the y, and let's talk a little bit about the x. So what they did was they designed 3 prisms. So 2 of these are being shot and about 200 yards away from the launch pad at 39A. They have a bunker, and it's a theodolite, it's a laser, and they're sending this up to a little prism, and it's called a poro prism because what it does is, as you shine a light, you can see it up here. You shine a light, and it bounces around inside the prism, and then it sends it back in the same direction, in the direction that it came from. So here, this this bunker is shining this light at a 25-degree angle up to a little sensor on the Saturn V. And so there are two prisms. So one is in this guidance unit, one is fixed and the other one is movable. So what they do is, obviously, as the Earth is rotating, these two prisms are going to diverge. And what they're able to do is tell the inertial navigation system to line up these two prisms, have the two lights line up, and they continuously do this for several hours before the rocket takes off. And then there's a third prism, and this one is pointed at the surface of the Saturn V. And the reason that they do that is not only is the Saturn V, the Earth spinning at 1,000 miles an hour, but the rocket, which is 365 feet tall, has a big sail area to it, and there's wind and stuff. So the rocket is actually kind of swaying back and forth. And they say about 30 centimeters to either side of straight up. The spacecraft is kind of, moving around. So between these three prisms, they're able to keep the x-axis in a place where they know where it is, and that turned out to be rather important. So I mean, I remember I was 10 years old when Apollo 11 took off, and I remember them saying they get down to about 15 seconds, and they say guidance is internal, and it's like, what the heck does that mean? Guidance is internal. So it turns out that here's the timeline for Apollo 11, and they're starting the terminal countdown, and this starts at 28 hours, so about a day before they take off, and then they have this hold, and then here you can see at 16.968 seconds, it says guidance reference release. And so what they're doing is, up until this time, the theodolite is sending the laser signal to continually update the rocket to say this is where X is. And when they get down to a little under 17 seconds, they no longer do that. And the rocket is saying, this is where I'm at. I'm not taking any more information from the ground. And I was interested in that, and I couldn't quite figure out why it is that they do that. I mean, why wouldn't you just continue to take that information until the rocket takes off? I mean, won't you get 17 seconds less error if you continue to do that? So I reached out to NASA, and one of the wonderful things about being a volunteer with the Jet Propulsion Laboratory is when you have a question, when there's something that you don't understand, you can pose it to people, and they pass it around, and they're wonderful. So the best guess that we have is that at about this time, at about 17 seconds before the thing takes off, there are some things happening in the rocket that make it so it doesn't really help you anymore to be sending this guidance information. So about 8 seconds, let's see. So we have a command start on the engine, on the Saturn 1C engine at about 9 seconds prior to liftoff. And so that's 9 seconds before the thing takes off. Well, before that, you have to spin up the turbo pumps. So there's a great deal of vibration that's going on in this thing. And, this little laser light, I would imagine the rocket's going to be moving a fair amount once all these big turbo pumps get going. So it's probably for that reason that they said when they got down to 17 seconds, they're like, okay, that's as much, assistance as we can get from the ground in terms of which way this thing is pointed. And so here you can see this is the instrumentation unit. It's about 3 feet tall, and it goes all the way around. It's at the third stage of the Saturn V. And here along the bottom, these are all the different kinds of pieces that are associated with it. But you can do updates when you're on the mission. So what we have here is is kind of a sextant for space, right? So right here, these ocular pieces, the astronaut, this is in the lower equipment bay on the command module. He'll look through this and align on a star, and he'll say, okay, mark, press a button, and it'll say, okay, uh, uh, the sextant is looking at this particular star, and they have maybe 30 reference stars. So the way this thing works is it has two controllers. One controller, you're able to move the spacecraft if you need to move that around, and the other moves the telescope. And so you move the spacecraft so that you can get the telescope to point at the star you want. And you can see over here on the right, that's one of those diskies. That's the input-output device for the computer. And you can see here on the bottom here, that's the computer right there. That's the Apollo guidance computer. And not only do they have the ability to this is kind of like doing Dead Reckoning, right? You're coming up with fixed points. You can not only do it in the command module, you can also do it in the lunar module. So here you can see the lunar module. These things here are the armrests for their elbows. And right here with that's ringed here in yellow, this is for sighting for their sextant. And they can do the same thing. They can point the lunar module at a particular star, hit the mark button, and tell the computer, okay, these are the angles between this star and and the horizon of the Earth, or here's the moon and here's the sun, and that'll help you with the navigation, figure out where you're at. So in terms of navigating in space, we have a couple of things that we can do. One is inertial navigation, and that's using accelerometers and gyroscopes. And then there's celestial navigation, right? You're taking angles off of known stars, and that helps you figure out where you're at. And then there's also using laser light and radio frequencies, light and microwave Doppler. So if you were to bounce a signal off of and you're not actually doing audio in space. I don't want to give the impression, because you can only do audio through you can't do audio through a vacuum, but a radio wave. When you bounce a signal off of something and then you bounce it again, and it takes more time or less time to get back to you, that tells you whether you're going towards it or away from it, and how quickly you're doing that. So that's the essence of Doppler, right? I mean, when the sound of a whistle from a train, when it becomes a higher or lower pitch, what you're hearing is an expression of what's happening. It's telling you that you're moving in a direction towards or away from. So there are a number of different things that people are doing in order to navigate in space. And so just when we think about the way in which we get places. So one-dimensional space, so we want to go from one place to another place. Well, if you had a compass and you said, okay, it's that direction, and you start walking, and it's one-dimensional space. That's all you need to know. You just need to know it's 270 degrees. So if you take a 270-degree heading, you're there. And then there's two-dimensional space. So we're on the surface of the Earth, and we've got a map, and we need to go, up 3 streets and over 1 to the right and stuff. You can determine your position with 2 dimensions. And now with 3 dimensions, like we're in an airplane, we not only want to know where are we in relation to the surface of the Earth, but also our elevation. So that's a 3-dimensional space. And we've gotten pretty good with one-dimensional space and 2-dimensional space and navigating in 3-dimensional space, right? But is that going to be the end of it? And so I'm just going to throw out there that maybe there's going to be more navigational requirements, things that we can't do well right now. So what if you had four-dimensional space? So let's say, for example, I'm looking at this little cube, the small one, and these things that connect the little cube to the bigger cube. Imagine that those are like arrows of time. So it may be that not only do you need to know the left, right, up, down, having the three pieces of three-dimensional space, but maybe there's also a time element or something else. I mean, let's say we wanted to travel through a wormhole or something like that. It might not simply be a question of coming up with one coordinate or two coordinates or three coordinates. There may be additional things that we have to learn in order to navigate. So that's all going to be interesting. And that's all I got for you. So questions and comments.
So let's give David a big virtual round of applause for another great presentation. And as he said, if you have any comments or questions, now is the time. Try to get your questions into the Q&A and your comments into the chat so we keep things separate, but, not the end of the world if you don't. So Suresh asks, if we consider a spacecraft as being in a cube, positions always have three points, I want to say. Is this based from someplace on Earth?
Well, don't get hung up on the spacecraft, on the shape of the spacecraft, because in terms of dimensions, all right, when we talk about being able to go from one place to another place, what you're asking is how many different values does it take for you to figure out how to get from one place to another? So when you're not trying to get someplace, let's say you're sitting in your spacecraft, you are a single point. Okay, now that point can be a big point or a small point, or it could be a triangular shaped spacecraft or whatever. But when we're talking about navigation, we're talking about, what would it take for you to be able to get from where you are to where you need to be? So if you wanted to go from where you are to some place that you can see out in front of you, what it is it's a line, right? It's a line between the point that you're at and the point where you want to go. So that's a one-dimensional, that's a line. But if you wanted to go someplace on the surface of the Earth, you might need to have two different points. And if you're like flying in an airplane, you not only need the left and right and the north-south, but you also need the elevation. So yeah.
Nancy says, wow, my mind is boggled. I have a much better appreciation for all that goes into any type of navigation.
Yeah.
And she thanks you.
Oh yeah, this stuff boggles me too. And I do these presentations not because I have a great deal of knowledge, because my background is not in science. I'm a retired flight nurse. So and this picture of me was taken at the Houston Space Center, and it was at their visitor center. I'm not an astronaut, never been an astronaut, but I like the picture. But yeah. When we have these talks, it's because I think to myself, wow, how could you possibly do that? How could you navigate in space when things are all going at different speeds and there's no place, there are no waypoints, and yeah, it's pretty cool stuff.
DJ would like clarification. What is a gimbal?
Yeah, so I was trying to remember I was looking up the interrelationship between gimbals and gyroscopes. So a gyroscope can have a number of gimbals, which how can I describe this? Because I remember reading that with Apollo, they were trying to decide whether or not something should be a 3 gimbal or a 4 gimbal gyroscope. And apparently when you're flying in an airplane, if you have 3 gimbals, if you have, I think they're kind of like shells. you could only go in a there are only certain attitudes that are possible. And one of the things that they wanted to do was they were talking about whether or not they needed a fourth gimbal. So my brother says that a gimbal is a mechanism typically consisting of rings that pivot around at right angles that keep an instrument such as a chronometer or a compass horizontal. Okay. Yeah, and interesting. Yeah, and so when they were trying to decide whether or not they should have three gimbals or four gimbals, it turned out that they went with the three ring thing because they said, it's unlikely that we're going to end up having a problem. And when you see on like the movie Apollo 13, and they say, we're floating near gimbal lock, it's actually possible in space to be going at an angle where you end up messing the thing up, and the whole thing kind of locks up. But it's rare, and so they kind of have that 8-ball on their instrument panel, and they have to stay away from that. I know that was a long-winded thing, but go ahead.
Yeah. Teresa says this was absolutely fantastic. Such an exponentially complicated subject matter explained so everyone can understand the issues.
Oh, great.
Thank you very much, she says.
Sure.
An anonymous attendee asks, from a PNT perspective, then this is all a precursor to GPS. These are the elements which led to its discovery? ?
Can they type in what PNT?
Sure. So anonymous attendee, if you want to clarify what PNT means, that'd be great.
Yeah, or just kind of come on. Yeah, so with global position navigation and timing. Okay, yeah. So just to talk about GPS for a moment. So using these hyper accurate clocks that they have on these satellites and they have on the ground receivers, they're able to and measuring the angles of the further away something is. So if you have a satellite that's traveling and it's 10 feet away and you're measuring an angle, or it's miles away, hundreds of miles away, thousands of miles away, the precision of the angle and the precision that they have with the timing enables you to be very, very precise of where that satellite is. And when you have a receiver in your phone, or you have it in your car, or you have it in your spacecraft, and you have 3 different satellites, or 4 or 5, it ends up triangulating, and you're able to find out exactly where you are in relation to these hyper accurate satellites.
Kathleen says, thanks so much, David. This was so interesting. You are a great teacher. You took such a complex subject and allowed me to understand it. I loved this talk, she said.
Oh, great. Great. Well, if you feel that way, then what I want to encourage people to do is to write to Robert and say, hey, invite him back, and I'd like to hear about this, and we'll see whether or not there's any agreement about what to talk about next. But there's all kinds of stuff related to aviation and space that I think is really interesting, and love to talk to you guys about it.
Yeah, and to David's point, and I don't mind folks sending me separate emails, but I also encourage you to fill out the feedback survey. And I believe it's the last question or second to last question. It does ask you for future, topics and subjects, and I would encourage you to, write any topics or subjects related to space that you'd like David to talk about in the future. Bob asks, do solar flares interfere with navigation in space?
Well, that's interesting. Well, I mean, when we think of solar flares, we think about a great deal of energy that's being emitted from the sun, and we know that it screws up radio communications. I don't know.
Yeah.
I don't know.
That's okay. Frank says, bravo, breathtaking. The problem solving that went into the Apollo program alone is absolutely astounding.
Oh,
Thank
yeah.
you again. And I will be watching this presentation, the recording of this presentation.
Great.
And Rich, I think, is going to wrap us up. Wants to know, were all the parts encased in resin to survive vibration?
Well, yeah. So that one of the issues with this computer is you have all these little wires, and when they initially were doing the computer for Apollo, this is just when they're starting to use transistors, and you got all these little wires that you have to solder into place. Well, so anytime that there's a wire that needs to be in contact with something, if you can encase that, then solder isn't going to break loose, and so as much of the wiring as they could pot. They called it potting. They would do that.
Excellent. And let me just confirm. Yep. So, David, I think we've addressed all comments and questions. Do you have any last words for the audience before we wrap it up?
It's an exciting time in space. I remember when I was growing up, I was just, I mean, the astronauts were my heroes, and I loved space exploration. And then for the longest time, for 135 flights, we had the space shuttle, and it just kind of went around the world, and even the International Space Station. I mean, it's probably interesting science, but it doesn't capture my imagination. But the kinds of things that are happening now with Virgin Galactic, and with Blue Origin, and with Orbital Science, and ULA, the United Launch Alliance, just launched on Monday, and SpaceX, and all that stuff is just fascinating. We're going back to the moon. Very cool stuff. So would love to meet with you again.
As would we. So let's give David a final virtual round of applause for a great presentation. Folks who are watching live, I'll look for an email for me tomorrow with a link to the recording, a link to a feedback survey, information about some other upcoming virtual programs that might be of interest. I hope everyone enjoys the rest of their day. And yeah, I'm still in mourning over Bill Belichick, David. So I'm still processing things.
I have some similar emotions. I figured that Tom and Bill would just finish their careers in Foxborough, and I don't know. I hope everybody has a happy and healthy 2024.
Yes. Let's have a great year. So thank you all so much, and hopefully we see David again in a couple of months. Have a great day, everyone.
Thank you.